So welcome back. The first speaker of our session is Bryn from the University of North Carolina at Chapel Hill. I study applied mathematics with Boyce Griffith and has done 2 practicums at Lawrence Berkeley and Lawrence Livermore National Laboratory. Let's welcome Bryn.
Okay, so yeah, I'm Bryn. I'm at UNC in Chapel Hill, and I'm going to be talking about my research dealing with Galerkin differences on mat grids with adaptive mesh refinement. So before I get into this at all, I'm going to take like a big step back to just really broadly what I do, which is I work on methods for numerical approximations to mathematical models. And so basically, we have these differential equations that give us these continuous models for different mathematical phenomena, and they're based off of theoretical principles from math and physics. And so when we're going about finding approximations to these, or discretizations, we start with the equation. So I do a lot of stuff in computational fluid dynamics. So usually what I deal with is some iteration or derivative of the Navier-Stokes equations. So none of this really matters. But the big gist is that these equations are derived from conservation laws in physics and math. And so there's a lot of different mathematical theorems and equalities and different properties that exist within these equations that are essential to modeling the flow of the fluid in my case. And so when we go about approaching how are we going to create a discrete approximation to this, one way to go about it is to think about preserving these physical and mathematical properties. And this approach is often called mimetic discretizations. And so the big idea is we're trying to find a discrete model that mimics these underlying properties, mathematical and physical, of the system. And one sort of example of a very common mimetic discretization approach is to use what's called a marker and cell or a mat grid. These were actually developed in the 60s at Los Alamos. And the main idea here is when we're discretizing our fluid, we're going to store our pressure values at cell centers and our velocity values at cell faces or edges in 2D. And what happens here is if we don't use the mat grid, or the staggered grid as some people call it, what ends up happening is the collocated pressure and velocity values, and when you apply these differential operators to them, you get all this strange coupling that kind of like undoes different neighbors and creates sort of impractical neighbors, and you end up getting these checkerboard instabilities, they're often called, which are just like these spurious fluctuations in the pressure that are not natural. They don't actually match what the system's doing in real life. So you end up having to add these like artificial viscosity terms to dampen out these pressures that we don't want. And all of this goes away when you just use a staggered grid. So this is just one example of how when we approach it from thinking about like, okay, how can we apply like conservation laws to our discretization, we end up getting these like naturally more stable discretization. And so the marker and cell grid, the mat grid, has become pretty standard in computational fluid dynamics, especially, well, when you're dealing with finite difference and finite volume codes. And some of the reasons for this are we get these mimetic properties that we really care about. The marker and cell naturally gives us a positive definite Laplacian. It naturally gives us this duality relationship where you have the divergence being the negative adjoint of the gradient. And there's all these different properties that end up working really nicely for our numerical approximation. But the other sort of side of this is that when we're doing numerical approximations, we often want to have a non-uniform grid. We want to be able to refine our mesh in certain areas of the fluid without having to refine everywhere, because that's just really expensive computationally. And this is called sort of broadly adaptive mesh refinement. And these two things are both very essential in computational fluid dynamics. But the issue is that when you add adaptive mesh refinement to a MAC discretization, you lose these mimetic properties. So you no longer have this symmetry in your Laplace operator. You no longer have these relationships between your divergence and gradient operators. And so this is sort of where my research question comes in. And I'm just going to talk a little bit about like what an application of this is. And so my first practicum was at Berkeley Lab working with John Bell's group, and they do a lot of fluctuating hydrodynamic research. And essentially, this is just fluid dynamics at nanoscale. So you've got your Landau-Lifshitz Navier-Stokes equations, which are the same as Navier-Stokes, but now we've added in these thermal fluctuations. And so essentially what that comes down to is our flux and our stress tensor are now not just the deterministic piece that we see at the macro scale, but we've added on this stochastic component, which ends up just being like a white noise tensor. And so the key here is when we add fluctuations to the system, we need to add them in a way that keeps the system balanced. And what that means is we don't want to add so much noise that it overwhelms the dissipation, and we don't want to add too little noise that the dissipation dampens it out completely. And so on a continuous in a continuous equation, this is called the fluctuating dissipation balance. And so when we're discretizing it, we need to discretely satisfy this balance as well. And so if we look closer at sort of the mathematics of these equations, it ends up coming down to we need to satisfy this balance by the relationship between the operators on the deterministic and stochastic components of the stress tensor. And that ends up being the divergence operator of the noise tensor and the Laplacian operator of the velocity. And so it ends up being that in order for this to be balanced, we need the thermal fluctuations or the divergence operator, if we go back, this divergence operator, we need that to be the square root of the Laplacian. And if that happens, then we satisfied our balance and we can actually run these simulations. But that requires an SPD Laplacian, which we don't have when we apply mesh refinement on these mat grids. So this is really easy if we're using uniform grids, but we really want to be able to use AMR or adaptive mesh refinement, and we just can't with fluctuating thermodynamics right now because there's no way to satisfy this balance because we don't have an SPD Laplace operator for mat grids. So that sort of leads to my research goal, is to develop this Laplace operator on mat grids with AMR that is SPD and has second-order convergence. A natural approach to this would be to look at it from like a finite difference or finite volume standpoint, where you're trying to come up with these stencils, and you're trying to construct these stencils in ways that give you consistency and also the level of convergence you want. And the simple way of saying is that this is just like really hard. It's a lot of guess and check. It's a lot of like, oh, you've worked out all the details, and then you get to this one random edge case and it doesn't work, and so you have to start over. And so that's sort of a hard approach, but it does give you the mat grid easily. Another sort of natural way to look at it would be from a finite element perspective, which finite elements, they just build in these mimetic properties. We get this symmetry that we want. We get all these relationships. And like maybe 20 years ago, this guy Guido Konschat, who is in Germany, he wrote this paper proving that there's this relationship between these lowest order discontinuous Galerkin finite element methods and a mat grid. And so there's this like cool, like, oh, there might be some overlap here, but the issue is that we get stuck at first order global convergence when we add in mesh refinement. And when we're using finite elements, when we want to go to higher order, the way finite element works is we're going to add internal degrees of freedom in order to get higher order approximation spaces. But now when we add these internal degrees of freedom, they no longer correspond to our mat grid structurally. And so this sort of leads to this new area of numerical methods that was just developed in the last 10 years by Jeff Banks and Thomas Hagstrom out of RPI, which is called Galerkin difference methods. And these are this energy stable difference method that's based on the Galerkin framework. And the idea is that when we're solving any sort of numerical approximation with finite difference or finite volume, we're essentially, we're implicitly employing these basis functions across this. We're interpolating these data points, these discrete data with these basis functions. And so we can take these basis functions and apply them to use the Galerkin projection method with them. And it ends up that if we use a really convenient choice for interpolatory functions is to use the Lagrange polynomials, because when we do that, we end up getting these properties that we need for an approximation space in a finite element framework. We get this partition of unity, all these other things that we really need in order to be able to use the Galerkin projection method. And so basically what this comes down to is in standard finite elements, we have our linear shape functions look like this, and then when we want to go to higher order, we add these internal degrees of freedom, but our shape functions still only have support over one single element. But when we go to this Galerkin difference framework, our linear shape functions look the same, but when we go to higher order, instead of adding nodes internally, we extend the support of our shape functions to cover additional already existing degrees of freedom. And so we end up maintaining structure that's compatible with the macgrid while being able to use these higher order sort of finite difference or finite element type methods. So I'm just going to sort of walk you through. I mean, a lot of this ends up being just like a lot of writing down math and making sure the equations work out and then coding it up. And so just big picture, this is a new field. And so my research started with just applying the Galerkin difference framework to non-uniform grids. And so that just meant looking at node-centered and cell-centered data and figuring out how do we handle hanging nodes, how do we make these two refinement levels communicate with each other so that we have continuity across the interface. And so this comes down to restricting the shape functions to only have support over their respective level, and then adding constraints to these. I've sort of highlighted the nodes along the interface that are like possible nodes we could be using in our constraints. And what it comes down to is there's a lot of different ways you could do it. And so you need to make sure that you're looking at the resulting condition numbers of the stiffness or mass matrices that you're producing with these, because a lot of these degrees of freedom end up having really small support, and so you can have sort of ill conditioning if you don't do it right. But in the end, it just comes down to doing a lot of math and making sure it works. But it's pretty straightforward. And then from there, I went and applied it to mat grids and non-uniform mat grids. And then we put it all together. So using this, there's this way to handle constraints and adapter mesh refinement in finite elements that's really simple, where you sort of encompass all of your constraints in this matrix, and then you just apply it to your standard stiffness operator. And so using that, we're able to get this simple sort of AX equals B linear system. And from there, we can extract a finite difference stencil for the resulting system. We can implement that in a finite difference code. So now we're in a code that we actually want to be working in, where we have these large finite difference or finite volume libraries. We confirm that it's positive definite. We get second order conversions for linear. We get fourth order for cubic. We also get sixth order for quintic. And so this is like a really exciting result. We've never been able to get even second order with mat grid adapter mesh refinement, and so now we're able to get much higher. One thing to note is that when we are sort of extracting these stencils and converting them to the finite difference, it gets really messy as you go to higher order and sort of tedious. But even the linear Lagrange basis functions give us second order, and those are very simple to implement, or relatively simple. Then from there, in order to implement this with fluctuating hydrodynamics, we need to recover the square root of this Laplace operator. We reverse engineer these sort of negative adjoint divergence and gradient operators. And then we also need to add in the pressure discretization for the Stokes solver, which you have to be a little careful with to make sure you don't lose stability. But all of these things sort of happen a little more naturally because now we're operating in this finite difference framework. And so that's sort of where we're at. We've got this working in a Stokes solver on like that I wrote myself. And so now I'm just working to try it out on some large codes. And so the real sort of roadblock here is that most FHD codes aren't even set up for adaptive mesh refinement. It's never been possible to do. So this is just a lot of sort of adapting these older codes to be able to even try this new methodology. But I'm working with John Bell's group at LBL to try out some different polymer chain simulations and looking at interactions with these ions. And so that'll be really exciting to see, because right now they're super expensive to run because we're having to use uniform meshes. Just want to thanks to my advisor, Boyce, who's actually an alumni of CSGF at UNC, and then I also work really closely with a postdoc turned professor, I don't know, in my group, David Wells, and then I did practicums with John Bell and also Bryn Olson, and I still work with John Bell. So, and then also huge thanks to CSGF. It's been so fun being part of this fellowship, and I met some of my best friends. So that's a wrap.